Hello everyone, it's Angela, and today we're going to be going over parts A and B on your pre-Tuesday workshop. Now from the problem, we know that lead has 4 stable isotopes, 3 of them and their natural abundances listed in the table. So let me color code the data. We have lead 206 with an atomic mass of 205.95 AMU and a percent natural abundance of 24.1%. We have these values for lead 207 and for lead 208. And part A is asking us the 4th stable lead isotope, and it's asking for its percent natural abundance. Now, this is a weighted average question, and the way that you approach it is that you have a component. In this case, let's start with lead 206. And each component is comprised of the fraction of the component, in this case 0.241, the percent natural abundance written as a decimal, and this is multiplied by the value of the component, in this case 205.95, the atomic mass of lead 206. And you add all the components together and you do this math for each component. So we do this for lead 206 or lead 207. With 0.221 times 206.95. We do this for lead 208 with 0.524 times 207.96. And we also will do this for our unknown isotope of lead. So we'll have Am for some atomic mass that it's going to be of lead. So you'll multiply it by its fraction, represented with an F, multiply by its atomic mass. And when you add all these components together, you will get the average value. And the average value in this situation is the average atomic mass of lead. You can get this from a periodic table, and it is 207.20. Now, for weighted average questions, all of the fractions will add up to 1. So we can use this to solve for our unknown fraction. So let's pull up our fractions that we know. We have 0.241 plus 0.221 plus 0.524 plus our unknown fraction, and this is going to equal 1. And so the only unknown in this equation is our fraction. Therefore, we can solve for it. And when we do, we find the fraction is equal to 0.014, or as a percent, 1.4%. So now we know our fraction, so we can substitute it in. So let me substitute in 0.014. And now in this equation, the only unknown is the atomic mass. Therefore, we can solve for it. And by doing some multiplication and addition, we find that the atomic mass is equal to 204.22 AMU, or that this is lead 204. Now that is part 1, or part A. Let's see what's going on with part B. In part B, we have that our sample of naturally abundant lead is mixed with an equal number of lead-210 atoms, and its atomic mass is given, and the question is asking for the new average atomic mass of lead. And so, in order to solve for this, we're going to need our expression from above, so let me bring it down. Alright, so we have our expression from before. This time I subbed in the atomic mass that we just solved for, and this entire thing is the sample of naturally abundant lead, and it's now mixed with an equal number of lead-210 atoms. That means that this sample now is half as much as it was before, because the other half is the lead-210 atoms. So we'll have 0.5 for the half multiplied by 209.96, the value of the component, and this will now equal a new average atomic mass, A. And so we know everything except for this A. And so if we multiply things out, and just note that this half is only applying to the fractions, not the value of the components. When you multiply this out, you will find that A equals 208.58 AMU. Now we'll just do a final check to make sure our fractions add up to 1. So we have all of our fractions from before, now multiplied by 1/2. And we will now add 0.5 to account for the lead-210. And if you do this addition, you will see that this does indeed equal 1. So that is our video for today. I hope you found this helpful. Thank you so much for watching.